Chapter 8 is our final final chapter in the notes, and it'll take us a few weeks to get through all the material here. And then there'll still be a couple of things to come in the course that aren't in the notes there, but there are a few extra kind of add-on things we're going to do at the end. This chapter is called Quadratic Residues, and it follows on from our previous couple of chapters on solving polynomial congruencies. Okay. So, in one word, kind of what quadratic residues is a quadratic residue is the term used for a number that has a square root in one of these modular arithmetic groups. So the study of quadratic residues modulo a prime is the study of elements of the multiplicative group congruence classes modulo that prime, studying the ones that have square roots. Because what we'll find out, what we'll discover today by doing some initial investigation of some examples, is that some of the numbers in the system have square roots and some of them don't. So we'll try and get a handle on that and understand some of the aspects of it and get a clue about some of the future results that we're going to go and prove about. Okay. But the first thing we're going to do to motivate what we're doing, we're going to return to some school mathematics, or A-level mathematics, or probably GCSE mathematics, I guess it is. And just to remind us of something which we'll then try and apply in our current context of modular arithmetic groups. Okay? So this thing we're going to remind ourselves of is solving quadratic equations. Okay, now we'll move fairly swiftly through this. It's a pretty basic topic, something quite familiar to you, but it's worth reminding ourselves of some key points about it. Okay? So this basic problem is to be able to solve some kind of quadratic equation like this, and let's say we're solving over the real numbers, over R. Okay? Finding the real numbers, being presented with an equation like this. So we'll take A, B, and C being real numbers, and we're trying to find if this equation has any solutions X. Okay. Now, there's a well-known, everybody kind of knows it off by heart, there's a well-known formula for the solutions. I'll put a little bit down here, which is the quadratic formula, which says that solutions are given by this thing, of course. You have minus B plus or minus the square root of b squared minus 4ac over 2a. Okay, everybody remembers that. Well, what you mightn't remember so clearly is the derivation of it, how to derive this formula. So we'll quickly go through that, and then we'll try and apply similar reasoning to a quadratic congruence modulo a prime number. Well, the first step in establishing this formula, and it's a little bit of a kind of a tiny trick, is to multiply both sides of the equation by 4 times a. And what that does is it changes the coefficients, but it's an entirely reversible step. And the point is, these two equations have exactly the same solutions. If you've got an x which satisfies one of these, it certainly satisfies the other one, and vice versa. So these two equations are logically equivalent. So we've multiplied both sides by 4 times a. And the reason that's good is because it allows us to do this kind of completing the square procedure. So that left-hand side there, 4a squared x squared plus 4abx, you can generate that by 2ax plus b, and you square it, so you get a 4a squared x squared plus 2 times the product of these two, so that's 4abx. Now you also get a b squared generated, which we don't see here, of course. So we'd want to immediately subtract that, get rid of it, and then you still got your plus 4ac here. Okay. And this is good because now we no longer have x in 2 places, an x squared here and an x over here. We've now just got one x located there, x to the power 1. So we just make this x the subject of the equation. Just chuck everything over to the other side. So this gives us that 2ax plus b is equal to the square root of b squared minus 4ac. And that's equivalent to, then you get the minus b over the other side, and you divide both sides by, of course we should say plus or minus the square root, and divide both sides by 2a. And that gives us our solution. Yeah. Okay. That's nice and familiar to everybody. So just see that again there. Just pass around the signature sheet. Now, I moved pretty quickly through that, and maybe a little bit too quickly. This step here, where we said 2ax plus b is represented by the square root of b squared minus 4ac. So I took the square root of both sides. But of course, we need to add a caveat to that. We say that this bracket is equal to the square root of this, but of course that only makes sense if this square root exists. And if we're restricting ourselves to talking about the real numbers, of course, not every real number has a square root. Now what's the condition? Which numbers do have square roots and which don't over the reals? If I give you a number, how do you know if it has a real square root? Positive. If it's positive, yeah. So all the positive numbers have real square roots, and they've all got two of them, positive version and a negative version. But the negative real numbers, we're restricting ourselves to talk. We're not going to bring in complex numbers. The negative numbers just don't have square roots. There is no real number such that when you square it, you get minus 1. It doesn't exist in the restricted universe of the real numbers. So this step is fine, provided you have this proviso, if it exists. But of course, it's not some big mystery whether or not it exists. All we do is this expression here, b squared minus 4ac, of course, we call the discriminant of the equation. So you just check the discriminant. If that's positive, that's a square root. You do have solutions given by this formula. If the discriminant is negative, there are no solutions over the reals. Okay? And finding square roots of a number, if I give you a positive number, well, okay, if the number is large, it might be awkward to get the square root, but there's no great difficulty in obtaining square roots. There are very efficient algorithms that will help us get square roots. So there's no great barrier to computing square roots. Okay. Well, that's all very well for equations of the real numbers. Let's try and repeat that. Can we apply these ideas? Can we apply these ideas to a quadratic congruence modulo a prime number? Well, let's just forge ahead. Let's just try and do it. Okay. So the first step was, okay, let's just make it clear what we're looking at here. We're looking at a quadratic expression being congruent to 0 modulo p. Now, in order for it to be a genuine quadratic expression, we'd require that we do actually have a genuine quadratic term here. So this a would have to be non-zero modulo p. So that means, assuming that a is co-prime to p, so that it isn't, well, no, sorry, assuming that a is not congruent to 0 modulo p. But if it's not congruent to 0 modulo p, that means we're assuming that p does not divide a. And if p does not divide a, since p is a prime number, that's equivalent to saying that a and p are co-prime. Greatest common divisor between them is just 1. So there's certainly no problem. Well, we can multiply both sides by a. Now, there's certainly no problem in saying that if the top is true, then the bottom must be true. The first congruence is true, then the bottom one must be true. We can multiply both sides. What I really want to say is that this expression is equivalent to the first one. Now, in order for me to put the other arrow on the other side here, to say that the bottom equation implies the first, is you must be able to go from the second equation back to the first one. So you need to be able to divide across by 4a again. And we can only do that if there's an inverse, if there's inverse modulo p for 4 times a. But of course, there will be, because the fact that p does not divide a means that a is co-prime to p. So it does have a multiplicative inverse. And does 4 have a multiplicative inverse modulo p? Well, assuming that p is a prime number bigger than 2, assuming it's not the first prime number, then p is odd. So 4 and p are co-prime as well. So 4 will have a multiplicative inverse. So if 4 and a have multiplicative inverses, so will 4a. So it is valid for me to make this a logical equivalence, assuming here that p is strictly bigger than 2. We're talking about that we're just excluding the first prime number. And that's no big loss. I mean, there isn't that much going on modulo 2. Modulo 2, there's only 2 elements, 0 and 1. Not a whole lot of interesting structure there. And to just consider quadratic equations over system 0, 1. There's not a lot going on. So that's no great loss. So that's fine. I can say that equivalence there. So 4a is invertible modulo p. Well, then we can complete, there's nothing stopping us completing the square, right, just as we did before. So 2ax plus b all squared minus b squared plus 4ac congruent to 0 modulo p. Well, let's just keep going. Now we've isolated x, we've reduced it from having 2 terms in x, 1 quadratic and 1 linear, down to just 1 linear term in x. Okay, well, it's squared there, but so we can just try and undo all that. So this is equivalent to 2ax plus b squared being congruent to b squared minus 4ac. So far, so good, just like the quadratic equation. Now, our next step, what we want to do is we want to take the square root of both sides. And we want to get rid of this square here. We'll take the square root of the left-hand side, so we'll just be left with 2ax plus b. Take the square root of the right-hand side. But up to now, we've never discussed square roots, that concept, in the modular arithmetic system, ZB. So, assuming we can do it, we can say that this is equal to 2ax plus b. Now, we tend to not use the square root symbol. When we're talking about square roots in the modular arithmetic symbol, we tend not to use the term square root. We tend to use the term quadratic residue or quadratic non-residue. And we don't really use the square root sign, just to not confuse it with real numbers. So I'm going to say that this says that 2ax plus b is congruent to u if u squared is congruent to b squared minus 4ac modulo. So instead of writing the square root of b squared minus 4ac, I'll say, well, it's equal to this congruence class, the congruence class of u, provided when you square u, you get b squared minus 4ac. So there's a condition attached to this. And then we can go on. Then we get, indeed, we get minus b. Well, let's say I'll put down plus or minus. That's not too hard to see. Because in modular arithmetic, if I square u or square minus u, I get to the same congruence class. Because minus 1 squared is always good. And I need to divide across by 2a, except when we're doing modular arithmetic, we don't talk about forming fractions of elements, so that we speak about the multiplicative inverse. So I multiply both sides by the multiplicative inverse of 2a, and I know that exists. The multiplicative inverse of 2a does indeed exist because of the comments about a before. The fact that p does not divide a, p is an odd prime, 2 is also co-prime to p, so 2 has it. So fine, this is all fine, subject to this square rooting operation I did here. Subject to the existence of this u. Okay. If such a u exists, then I can form my x with this expression here, and either of these x's, given by either of these choices of plus or minus here, should give a solution of the quadratic equation. Okay. So this natural example of asking for solutions of a quadratic equation over the integers modulo p, this naturally introduces this idea of square roots or quadratic residues. Okay. So what we say in the language we use in number theory is that this number, or any number, is a quadratic residue if it has a square root. If it has a number such that when you square the other number, you get back to the first. Let me say the first one is a quadratic residue. The definition, we say V is a quadratic residue modulo P if there exists a U such that U squared is congruent to V modulo P. We don't even know at the moment, we don't even know if any of these exist at all. But here's the terminology, quadratic residue, and its V is a quadratic non-residue if there does not exist such a U. Because if there wasn't any number U which I could put there, such that when you squared it, you go back to B squared minus 4AC, then I wouldn't have been able, this line here makes no sense because there is no U existing to give you that. So there would be no solutions to it. So this is a way to motivate the introduction of this concept, the concept of numbers having square roots. And it prompts us to try and investigate it. Okay? Find out, do square roots modulo a prime always exist? If they do exist, how many of them are there? If we know they exist, can we obtain them efficiently? If somebody gives you a congruence class, can you A, find out if that congruence class is a quadratic residue, if it has a square root? And even if you can tell it does have one, can you find it efficiently? And is there any more efficient methods for finding them than just trying all the possibilities? So, lots of questions to answer about these. Which we'll go on to investigate now. But any initial questions just about that definition or just about that treatment of the quadratic congruence? Anything there I can clarify for you? So this is fine. This is a good treatment of a quadratic congruence. It gives you a formula for the solutions, provided that this number U exists, and provided you have some reasonable way to obtain that. So before we jump into all the theory, before we start proving general theorems about this, we'll want to investigate a few examples. So we'll choose some prime numbers. We'll try and see if there are quadratic residues, how many of them, and just have a look and see what's going on. Okay. So the first example will go quite small. Look at the prime 5. Okay, you should be able to identify everything that's going on. It's not too complicated. There's only 4 non-zero congruence classes, 4 multiplicative congruence classes. 1, 2, 3, 4. 1, 2, 3, 4. When you're working modulo 5. Now, which of these are quadratic residues and which are not? Which of them have square roots and which of them don't? Well, we could sit there staring at them, but there's quite a quick way, when there's not too many elements around, is just start squaring everything. Start squaring everything and see. So this operation is squaring the elements. So when you square 1, you get 1. When you square 2, you get 4. When you square 3, you get 9. But 9 modulo 5 is, of course, 4. And when you square 4, you get 16. But 16 modulo 5 is 1. Okay? So 1 squared is 4. Sorry, 1 squared is 1. 2 squared is 4. 3 squared is 4 again. 4 squared is 1 modulo 5. So it's clear here that there are 2 quadratic residues modulo 5, 1 and 4. And 2 and 3 are non-residues. There is nothing, no integer, that when you square it, modulo 5, you get 2 or 3. They just don't exist. So if we tried to solve a quadratic congruence modulo 5, and if this b squared minus 4ac, if that was 2 or 3, the thing would grind to a halt here, okay? Because there would be no such, sorry, that's the quadratic equation. Wrong example. This one here, if my b squared minus 4ac came out as 2 or 3 modulo 5, I wouldn't be able to proceed any further, because there would be no u that I could put down there. That when you square it, you got back to 2 or 3. So 1 and 4 are residues. Modulo 5. Quadratic residues modulo 5. And 2 and 3 are not. So two residues, 2 non-residues. That's kind of nice. Half and half. Upon reflection, hang on a minute. It should have been pretty obvious that 1 and 4 had square roots. Because like 1 always has a square root, doesn't it? So when you square 1, you always get 1. And 4, any integer, any congruence class that's represented by the integer 4, that always has a square root as well. Because when you square the integer 2, you get to 4. Of course, p is kind of 5. 5 is kind of quite small in order to see anything interesting. So let's maybe go up a little bit. Let's go to 11. So that was example 1. And now let p equal 11. We're going to prime. So there are 10 congruence classes modulo 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, I pose the same question. Which of these are residues and which of these are not? Now, some of them we can probably guess ahead of time, or we should just realize straight away that 1, 4, and 9 will be quadratic residues. Because we can square root those over the integers. 1 squared is 1, 2 squared is 4, and 3 squared is 9. So that will be the same modulo 10. That will also work modulo 10. But what about all the other numbers? Well, again, if we square everything, we'll see what's happening. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, but modulo 11, 16 is 5, 5 squared is 25, but modulo 11, 25 is 3, so it's 22 plus 3. Of course, I don't need to sweat it working out the other ones, because look, 6 is the minus of 5, 7 is negative 4, 8 is negative 3. So the rest of this list is just going to be the palindrome of, or it's just going to be the list I've just written out, except in reverse. This is going to be 3, 5, 9, 4, 1. Okay? So this is squaring everything. Now, of course, we do indeed see that 1, 4, and 9 are squares. They look like square integers anyway. But we also find that 5 and 3 are squares. Okay? So if you square 4 or 5, you get respectively 5 or 3. But 6, 7, 8, and 10 are not residues. So modulo 11, the residues are 1, 4, 9, 5, 3. These are residues. But the other ones, the missing ones, which are 2, 6, 7, 8, and 10, are not. Anything nice about that example? Again, it's half and half, yeah? We have an even split. 5 of the, so there's 10 congruence classes, modulo 11. 5 of them are residues, 5 of them are not. It's kind of nice. Let's look, we should just think, just because we've seen it twice that you get an even split. Shouldn't perhaps think, just based on that, it should always be true. So let's look at a couple more examples. So now let p equals 13. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the congruence classes modulo 13. Okay, let's quickly square them all. Pre-prepared this just so I don't tie myself up in knots. So I got 1, 4, 9, 3, 12, 10. That's all you need to work out because 7 is minus 6 modulo 13, 8 is minus 5. So when you square these, you're going to get the same thing as when you square their minuses. So we get 10, 12, 3, 9, 4, and 1. So again, we expected to see 1, 4, and 9 as residues because they are square integers anyway. But now we see that 3, 12, and 10 are residues also. The modulo 13, the residues are 1, 4, 9, 3, 12, 10. Again, there's 6 of them, half of the total. And the other ones which aren't there, which is 2, 5, 6, 7, 8, and 11, are non-residues. Again, we're seeing half and half, so this split is looking pretty good. But aside from that, we're not seeing any very regular behavior. For instance, modulo 5, 3 was not a residue, but it is a residue modulo 11 and 13. 2 was never a residue in any of these examples. 5 was a residue modulo 11, but it's not modulo 13. 10 wasn't a residue modulo 11, but it is modulo 13. So there doesn't seem to be any extremely regular behavior. Okay, the half and half split is, of course, very regular so far. But, okay, 1, 4, and 9 are always residues because they're square integers anyway. Anything is going to be 1, 4, and 9 are going to be residues modulo anything. But the non-square integers, there doesn't seem to be any very regular behavior. Sometimes they are, sometimes they aren't. Okay, one final listing example like this. Modulo 17. I won't even write them. I won't square them all out. So modulo 17, if you work it out, the residues are, again, it's a 50-50 split. Residues are 1, 2, 4, 8, 9, 13, 15, 16. So we expect to see 1, 4, 9, and 16 because they're square integers. The other ones crop up there. And the non-residues are all the other ones. So non-residues are the remaining ones. 3, 5, 6, 7, 10, 11, 12, 40. So 8 and 8. So our initial investigations throw up a few things. First of all, we always see half and half. So we'd be ready to conjecture now, or to start to believe it, or start to very strongly suspect that modulo any prime, half of the congruence classes are going to be square, are going to be residues. Half of them are going to be non-residues. Aside from that, there is no trivially easy to say thing about the behavior of the things that aren't obviously squares. But the 1, the 4, and the 9, and 16 are obviously residues because they're square integers themselves. The question of, why 8 is the residue modulo 17, and why it's not a residue modulo 13, and why 7 is not a residue of either of them. Is there any way to explain that? That's not so obvious just from looking at those results. Now, in some ways, when we looked at the real numbers and the equivalent concept of number of square real numbers and numbers having a square root, the division was into positive and negative numbers. Positive numbers have square roots, negative numbers don't. Here we're looking at residues and non-residues. We get this even kind of split. So we wonder about, is there any other way that these mimic the behavior of positive and negative numbers? Would it be a reasonable thing to say that the residues act like positive congruence classes modulo 17, and the non-residues act like negative congruence classes? Is that a reasonable thing to say with respect to multiplication, with respect to the operation of multiplication? Well, I prepared some tables here. So looking at modulo 13 and modulo 17. Any questions so far about those examples? Is everybody clear on the concept?
Yeah, residue.
Residue.
I don't get it.
You don't get it. So modulo 13, these numbers, the numbers we're seeing here in the second row, these we got by squaring the top ones. Modulo 13. But these are special. Special because they have square roots. Square root of 12 is 5. Talking modulo 13. Yeah. So these numbers here, we've listed here, modulo 13, these all have square roots. But these numbers don't.
How do you get square root of 12 to be 5?
Because when I square 5, I get 12.
Okay, so 5 better.
Yeah. It's like saying that 5 squared is 12 is the same as saying that the square root of 12 is 5. Yeah. Yeah. Now, for real numbers, it's very easy to understand what's going on. Positive numbers have square roots, negative numbers don't. The question here is, in these different systems, these multiplicative systems, modulo prime, what's going on here with why some numbers sometimes have square roots and other numbers other times don't? So, why is it always an even 50-50 split? One way we might try and discover something is to look at the multiplication table. So I prepared this. This is the multiplication table modulo 13. Okay. Sorry, that's modulo 17. Let's look at this one first. Modulo 13. So these are all the elements 1 through 12. And that's what the multiplication table looks like. Now, okay, I'm not claiming anything is going to jump out immediately there. But this is modulo 13. So the residues are 1, 4, 9, 3, 12, and 10. So those are the residues. Well, they're kind of spread out there. it might be a better way to look at this table is to group all the residues together and then all the non-residues together. So that's what I've done a second time. Of course, I'm not asking you to take this table down. Time. So those are, but I've grouped the elements here into residues, non-residues. So in each entry of the table here, we see the products. And you've got residues, non-residues. What do you notice about that table? We do notice something striking about this multiplication table. Anybody see any structure there? Any features of that, of the entries in the table?
There's a transpose.
Well, it is symmetric, certainly, yeah, because it's a multiplication table. Yeah, the multiplication is commutative. So yeah, the transpose of the whole table is itself. That comes from the fact that multiplication is commutative. But anything arising from the way we've grouped the elements there. Well, you see, when we multiply residue by residue, we get all these numbers, but look at every number appearing there is a residue. When you multiply a non-residue by a non-residue, then you're over here in the table. Those are all the residues as well. 1, 3, 4, 9, 10, 12. And when you multiply non-residue by residue, this area down here and this area up here, you get 2, 6, 8, 5, 7, 11 in various positions. Those are all the non-residues. So we're starting to see something. When you multiply a residue by a residue, you get a residue. When you multiply a non-residue by a non-residue, you get a residue. But when you mix them, when you multiply a non-residue by a residue, you get a non-residue. So if you organize the table into residues and non-residues, when you do the multiplication, residue by residue gives residue, non-residue by non-residue gives residue, and non-residue by residue gives a non-residue. So the multiplication table has this block form, block structure. That was modulo 13. Well, exactly the same thing happens at other examples. So that would make us feel that the exact same thing would happen all the time. So this is the multiplication table modulo 17. So as you saw a few moments ago, when we worked it out, modulo 17, the residues were 1, 2, 4, 8, 9, 13, 15, 16. That's all these numbers here. Those are residues. Those are the non-residues, and we've used the same ordering on the rows as well. Residues, non-residues. And we see exactly the same thing in this multiplication table. Residue by residue is residue. Non-residue by residue is non-residue. So the entries here in the bottom left of the table come from the set 3, 6, 12, 7, 10, 5, 11. And various others. Those are all the non-residues. 11, 14. But when you multiply non-residue by non-residue, you get one of the residues. 1, 2, 4, 8, 9, 13, 15, 16. That's all these entries here. Okay? So again, we see the structure that residue, non-residue, residue, non-residue. When you multiply them by one another, they have the multiplication table has that form. Okay, any questions about that? Things I could clarify for you. So this was the introduction to it. So what kind of things are signposted for us there? So for next time, so I'll be seeing you on Friday for another lecture, and then in the weeks after that, here are some of the things we're going to be investigating. Are half of the elements in ZP, the multiplicative group, always residues? And half non-residues? Okay, that's going to be one of the first general results we proved. The system ZP is always made up of half residues and half non-residues. The other one is it always true that residue times residue equals residue, and non-residue times residue equals non-residue, and non-residue times non-residue equals residue? Is that always true, modulo P? See, what does that remind you of? This reminds us of, remember I suggested that maybe we could think of residues as being positive numbers and non-residues acting like negative numbers. But of course, you're very familiar with the fact that over the real numbers you have positive times positive is positive. Negative times positive is negative. And negative times negative is positive. That should be an equals there. Okay. So residues and non-residues do seem to be mirroring that multiplicative property about positive and negative numbers. And perhaps the most mysterious question, so these are things that we perhaps believe are true from looking at our examples. But the harder kind of problem which was raised by looking at the individual elements was, given an element n in ZP, is n a residue? Question mark. Okay, we can find out the answer to that question by a naive means, which we've done so far, of looking at all the elements in ZP and squaring them, just see which elements crop up as being residues. So that's like a kind of a trial and error way of answering this question. Is a given element a residue? Is there any other way that we could start to see, maybe understand the answers to this question? Why is n sometimes a residue? Why is it sometimes a non-residue, modulo different primes? And if it is, can we obtain its roots? If we do decide it's a residue, is there a non-naive way of obtaining the elements that are its square roots, obtaining the other numbers such that when you square them, you get n? Those are kind of harder questions, or more mysterious questions that are floating around from the examples that we looked at. Okay. So I think next time on Friday, I think we'll certainly see proofs of the first two, and the kind of rest of the chapter is mainly centered around understanding the kind of answers and the kind of structure that's involved in this first question. Given an element, a random element of one of these systems, how can you determine whether it's a residue or not? Because ultimately, that's what lies behind obtaining solutions to quadratic equations over these systems. Okay. Okay, we'll leave it there for this afternoon, and I'll see you again on Friday.